All right, let's dive in. You know, every single piece of technology we use today, from the phone that's probably in your hand right now to the massive supercomputers that power our world, it all boils down to one fundamental secret. A secret that happens at the atomic level. And today, we're going to uncover it. So have you ever really stopped to wonder what's going on inside a computer chip? I mean, how does this tiny little sliver of silicon do what it does? How does it calculate, remember things, and for all intents and purposes, think? It seriously feels like magic, but I promise you, it's just really, really cool physics.
And the answer, the very core of it all, isn't found in some crazy complicated circuit diagram, not at first anyway. Nope, it's way, way smaller than that. The real secret is hidden deep down, inside the atom itself.
That's right. If we want to understand how a complex processor works, we have to rewind all the way back to the very beginning. We've got to start with the fundamental building blocks of, well, everything. We have to start with atoms.
Okay, so you probably remember this from a science class somewhere along the line. An atom has three main parts. You've got your protons and neutrons packed into the center, the nucleus, and then you have the electrons just buzzing around the outside. Now, for what we're talking about today, for the entire field of electronics, we can kind of ignore two of those. There's really only one particle that matters, and that is the mighty electron.
And to be even more specific, we really, really care about a special type of electron called a valence electron. These are the ones on the absolute outer edge of the atom. You can think of them as the adventurous ones, the explorers. Their ability or inability to get up and move around is what determines whether a material can carry an electrical current or not. These little guys are the heroes of our entire story. Which brings us to the star of the show, silicon. And no, it's not just famous because of Silicon Valley. There's a reason it's the chosen one. First, it's the second most common element in the Earth's crust, which means it's super abundant and cheap. But more importantly, its atomic structure is just perfect. It's uniquely suited for building the electronics that run our lives.
So what is silicon's big secret? It's this number, 4. That's it. Silicon has exactly 4 valence electrons. Not 3, not 5, 4. And that number, that simple little number, is the magic key that unlocks everything else. See, because silicon has 4 of these outer electrons, each silicon atom is looking to link up with 4 of its neighbors. It shares 1 electron with each neighbor, and this sharing creates what we call a covalent bond. It's a super strong, super stable connection. And when you get a bunch of them together, they form this perfect, predictable grid, a crystal. Okay, now here's where it gets really interesting. Temperature changes everything. If you could cool silicon down to absolute zero, as cold as it gets, all those electrons would be locked rigidly in their bonds. Nothing could move. At that point, silicon is an insulator. It won't conduct electricity at all. But just by warming it up to room temperature, you give the system a little bit of energy. And that's just enough for a few of those electrons to get excited, break free, and start wandering around. And in that instant, it stops being an insulator and becomes a semiconductor.
So how do we visualize this? You know, this idea of an electron being stuck versus being free? Well, physicists have this concept called energy bands, which can get a little abstract, but don't worry, there's a really simple analogy we can use that makes it all make perfect sense.
First up, you've got the valence band. The easiest way to think about this is that it's the electron's home base. It's the default energy level where it's just hanging out, attached to its atom, stuck in that crystal grid. It's comfortable, but it can't really move around or get any work done. And then you have the conduction band. This is the freedom level. If an electron can get just enough of an energy boost to jump up to this band, it's no longer tied to one specific atom. It's free to roam through the whole material. And what is a freely moving electron? Well, that's an electrical current. So the most important part of this whole picture is the space between them. We call this the band gap. You can think of it as the price of admission. It's the exact amount of energy an electron has to absorb to make that leap from its home in the valence band to total freedom in the conduction band. And this brings us to that simple analogy. Just picture a building. The valence band is the ground floor. The conduction band is the top floor. And that band gap, that's just the flight of stairs an electron has to climb to get from the ground to the top. To climb stairs, you need energy. It's the exact same for an electron.
So why is this building analogy so helpful? Well, it perfectly explains the difference between a conductor, like a copper wire, a semiconductor, like a computer chip, and an insulator, like a piece of rubber or a rock.
It all comes down to the size of the band gap, or in our analogy, the size of the staircase. A conductor has no staircase, a semiconductor has a small one, and an insulator has a giant one. And that single difference defines everything about how they handle electricity.
Let's start with conductors, like copper. In this case, the ground floor and the top floor are basically at the same level. The bands actually overlap. There are no stairs to climb. Electrons can just wander back and forth with almost zero effort, which is exactly why electricity flows so easily through a wire. Now for our hero, the semiconductor. Here, there's a small, very manageable flight of stairs. It takes a little bit of energy to get an electron to climb it, maybe from some heat or from applying a voltage, but it's totally doable. And because it's possible, but not automatic, it means we can control it. We can turn the flow of electrons on and off. And that control, that is the absolute foundation of all computing. And finally, we have insulators, like glass or rubber. In these materials, the band gap isn't a staircase, it's a massive cliff. The amount of energy an electron would need to make that jump is just enormous. So for all practical purposes, they're just stuck on the ground floor forever. No current can flow.
So why have we been digging into all this atomic-level physics? Why does any of this matter? Because this single, elegant concept, controlling whether an electron can jump across a small band gap, is literally the foundation of the phone or computer you are watching this on right now. Every single one of these things, all of this tech, is only possible because we figured out how to manipulate that band gap. The transistors that act as tiny switches in your computer CPU, they're just controlling that jump. LEDs and solar cells, that's all about electrons jumping up or falling down across that gap. It is not an exaggeration to say that this one idea powers our entire modern world.
So if there's one thing you take away from all this, let it be this sentence right here. This is the whole explainer boiled down to its essence. In a semiconductor, we can make electrons move from the valence band to the conduction band across a small band gap, and that is what allows for controlled current flow. That's the secret.
So we've gone on a journey from a single atom all the way up to the phone in your pocket. You now know the fundamental principle that makes it all possible. But this, of course, leads to a new and pretty fascinating question. For the last 50 years, we've just been making these atomic switches, these transistors, smaller and smaller and smaller. So now that you know how it works, how small can we actually go?